Okay, I can just start. Yeah, sure. Okay, thank you to the organizers. I'm very happy to be here for the first time in Taiwan. It's a pleasure. Um, okay, so this is going to be a mini course on the existence theory of minimal surfaces. So minimal surfaces are extremely important objects in differential geometry, and they have been studied since the 1700s, but they are very hard to find. For instance, one of the major results in the theory was proven in the 1930s by Douglas and independently by Rado, was the solution of the Plato's problem, that given any closed curve in Euclidean 3 space, there is always a minimal surface that has that closed curve as the boundary. So it's really a major thing in the field. So I'm interested in the case where the surfaces have no boundary, so they are closed, and in general Riemannian manifolds. So how do we find the surfaces? So it turns out that this is actually a much harder question, because it's not a question of minimization like the Plato's problem. So most minimal surfaces are not area minimizing. And I have been working on the subject for the past 6 years with my collaborator Andre Neves. So developing some tools, proving some results. Finally, a few months ago, we actually made an important discovery. So we were able to prove that for most geometries, so for most Riemannian metrics, there are lots and lots of minimal surfaces. And there are so many that they are even dense in the manifold. And there's also an equidistribution result. So in this course, I'd like to, of course, I won't have much time to enter into details, but I'd like to give an overview of the theory. I'd like to state these results. And I'd like to prove the main tool in the proof is what we call this Weyl law for the volume spectrum. So I'd like to give a proof of that result here in this course. And then during my talk, in my talk during the week, I will talk about the proof of the denseness result and the equidistribution result. Okay, so let's get started. So for motivation, I like to start with geodesics. Okay, so the first, I guess the starting point of the whole thing is the theorem of Burkle, 1917. So he proved that every Riemannian two-sphere say S2 G contains a non-trivial closed geodesic. So it's going to be a smooth closed geodesic. By non-trivial here, I mean that it's non-constant. So this actually answered the question of Poincaré. Poincaré asked whether every two-sphere contains a closed geodesic. So the answer is yes. And Birkhoff was the first guy to prove that. So, of course, one always has the constant curve is a closed geodesic, so we want to like to prove there exists a non-trivial one. And one reason why this is actually an interesting problem is because there are two different strategies here in proving this result. So first, one can think about, a geodesic is an orbit of the geodesic flow. So a closed geodesic is just a periodic orbit. So one can think about dynamics there. But also, closed geodesics are also critical points for a natural function, the length functional. Right? So the first derivative of the length for every variation is equal to 0. So one can take the point of view of calculus of variations. So there are these two different approaches. Actually, it turns out that one can prove this using the calculus of variations. So I'm going to talk about the proof. So first, of course, let me just recall why this is true. Well, this is classical formula called the first variation of length. So if you give me a curve C, say S1, into some Riemannian manifold, I can compute its length. This is just the integral of the velocity vector. This is the length. And then if you give me, if you vary the curve, so if you give me a variation of my curve, then I can compute the first derivative of, so with respect to S, of the length, say when S is equal to 0. And this turns out to be the integral of the scalar product between the geodesic curvature vector of the curve and the velocity of the variation. I'm assuming here that my curve maybe is parametrized. This is with respect to the arc length measure on the curve. So K here is just the geodesic curvature vector. And then of course from this formula one sees that vanishing of this vector, and this is a geodesic equation, it's just equivalent to the property that the first derivative of the length is equal to 0 for every variation of C. So closed geodesics are critical points of the length function. Okay, so one remark is that if instead of a sphere, if we have some Riemannian manifold that has non-trivial fundamental group, then it's actually easy to show such a closed geodesic exists. So if pi 1 of the manifold is non-trivial, then for every non-trivial homotopy class, so for every element A in pi 1 that is non-trivial, I can find there exists a closed geodesic say gamma belonging to A such that the length of gamma is equal to the infimum of the lengths of all curves belonging to A. This is a positive number. Okay, so if I choose, say, some curve that is homotopically non-trivial in the manifold, then you just minimize the length over all curves that are homotopic to this original one, and that number is going to be positive, and it's going to be achieved as the length of a closed geodesic. So it's length minimizing closed geodesic. Of course, this approach will not work for S2 because every curve in S2 is homotopic to a point. So this would give you 0. So it becomes a non-trivial question then, construct such closed geodesic. So the idea Burkle had, was really a very important idea, was that one cannot solve this by minimization, but actually one can do it by a minimax. Okay, so let me just explain what minimax is. This is just an illustration here. Later, I will explain the analogy with the problem of geodesics. But for the moment, let's just say that I have some surface which looks like this. And say I'm trying to study some function f, which is going to be the height function in this case. This is the real line. Then I like to find critical points of the height function over the surface. Of course, there's a point here, x naught, It is the minimum point of f, so the critical value of C naught is just the infimum of f x x. Say the surface is lambda, x and lambda. So if you want to detect this critical point, you just choose a minimizing sequence and take a limit. But of course, there's a non-trivial critical point here, say x1, which is actually of saddle type. So it's not a minimizing critical point. So this corresponds to some critical value C1. And then the question is, how do we detect this critical point? So the idea is the following. So you choose a loop. Maybe I like to use some color. So the idea is that you choose a loop that goes into the hole of the surface, say sigma naught. So choose say sigma naught from the interval 0, 1 to lambda, some curve such that sigma naught of 0 equals sigma naught of 1. This is equal to x naught, and such that the homotop class of sigma naught, this means the homotop class, is non-trivial as an element of pi 1 of lambda, the surface. We choose a loop that goes into the hole of the surface, and then what you like to do is, for each such loop, you like to look at the point where the function achieves its maximum, so you maximize the function over such a loop, and then you minimize this number over all loops. So try to find the optimal way of going through the hole of the surface, and then you find out that the best way is to go through x1. So this is saying that critical value C1 is actually a minimax. So C1 can be obtained by doing the following thing. So it's going to be min-max, so if sup. So for every loop sigma that is homotopic to sigma naught, so this means homotopic relative with fixed boundary value 0, 1. So for each yellow loop in the picture, I maximize the function over that loop, and then I minimize over all loops, and I get C1. Okay? So this is what minimax is. It's a way of detecting non-trivial critical points by using the topology of the space, lambda. So one remark here that will be important later, not now, but later, is that the Morse index, so the index of the critical point, so the index is just the, if you look at the second variation, and then it's the index of the second variation quadratic form. So in this case, it's equal to 1, because there's one-dimensional parabola pointing down, and we are able to detect this critical point by doing a minimax over a one-parameter family. Okay, so later we're going to be talking about multi-parameter families. So the relation with the Morse index will be important. For now, let me just point out this fact. Of course, the Morse index of the point x naught is equal to 0 because it's a minimizing point. Anyway, this was the idea of Birkhoff. Well, Birkhoff knew about this way of producing critical points, and then when you look at this problem, he just observed that it's really basically we are in that kind of situation. So here's the analogy. So now you take lambda. It's going to be up. I'm now back to the problem here. So lambda is going to be the space of all closed curves in S2. So the functional f is going to be the length functional. Of course, critical points for the length functional in the space of closed curves are closed geodesics. And then x naught is the trivial critical point here, is just the constant curve, which minimizes the length. And then x1 is going to be the non-trivial closed geodesic. So I have to, so the question here is, what is sigma naught? So what is the yellow loop in the picture? So this is the notion of sweep out. So suppose this is the shape of your sphere as to with the metric G. Then one does the following thing. For every map F, I should choose a different, let's say phi. So for every map phi from S2 to itself of degree equal to 1, so this is a non-trivial map. So say this is the x3 direction. This is the standard S2. So what one does is the following thing. Where's my color? My color is here. So I take the standard foliation of S2 by round circles perpendicular to the x3 direction, and I look at the image of these curves under my map phi. The map phi doesn't have to be injective, so maybe something like that could happen. Anyway, this gives me a one parameter family of curves that sweep out my S2. So this is my sigma naught. Okay, for every t in the interval 0, 1, I associate, let me call it sigma sub phi of t. This is going to be the image under phi of the curve x3 equals to 2s minus 1 to t minus 1. So t goes from 0 to 1. So this is sigma sub phi is what I call a sweep out. It's a one parameter family of closed curves in S2 that comes from a degree 1 map. And of course, once we have the right notion of sweep out, what I like to do is to do my minimax. So I'll define L bar to be nymph sup. And then for every map phi of degree 1 from S2 to itself, so phi goes from S2 to itself, I look at the corresponding sweep out and I maximize the length. So I maximize the length of sigma phi of t. T goes from 0 to 1. And then I minimize over all phis. So this is my number L bar. And then one proves two things. First, that L bar is positive. And secondly, that there exists a closed geodesic. Gamma contained in my Riemannian sphere with the property that the length of gamma is equal to L bar. And that's how one proves this result. So let me explain how that is done. So going back to this analogy here, in this situation here, I would like to detect this critical point x1. So there's one thing one can do, which is very natural. say some kind of efficient way of detecting this critical point, what one can do is the following. So you choose your favorite curve that goes into the hole of the surface, and then once you have that curve, what you like to do is you apply the gradient flow of minus the function. Okay, so here in this picture you have this vector field pointing down, which is the gradient flow. Of course, the gradient flow is 0. This vector field is 0 at the critical points, right? It's pointing down. So you're going to flow your curve with time. And because this curve is homotopically non-trivial, it cannot collapse onto x naught. So it has to get stuck. And where it gets stuck is at the critical point. So you flow your curve, and then at some point in the curve, in the yellow loop, we'll have to converge to x1. Okay, so the question is, what is the gradient flow there? This is the eraser, right? So Birkhoff came out with a flow. We call it Birkhoff's curve shortening. It's actually a very simple thing to do. So imagine that you have a curve, say C, which is parameterized by the circle, of course, in my manifold. Let's say the length of the curve is bounded, say maybe by 2 times L bar, which I can always do. Then if I subdivide here my circle, say this is parameterized proportionally to arc to the arc length. So if I subdivide my circle many times, so say R segments of equal length, but R is very large, then when I look at the image of these points, 2 successive points are going to be very close to each other in the manifold. So there will be a unique minimizing geodesic connecting these 2 points, right? Because it's inside some convex ball. So you replace your little piece by a geodesic. Okay? So you do that for every successive pair of points. So you replace your curve by a broken geodesic. And after doing that, I'm going to do it again. So I'm going to look now at the midpoints of this new curve. Again, this is going to be points which are very close to each other. So there will be a unique minimizing geodesic connecting these 2 points. So maybe I'll use some color here. Something like that. And this new curve, I call it D of C. The map D is Birkhoff's curve shortening. So the length will go down. So what are the properties of this map D of C? The first main property is that the length of D of C is strictly smaller than the length of C, unless C is a closed geodesic. Of course, in that case, the curve doesn't change and the length is the same. Okay, this is why, well, if the length, of course the length will go down, but if it doesn't decrease strictly, it's because first, my original curve happened to be a broken geodesic, so there was no replacement. Once you know the initial curve was a broken geodesic, you look at the midpoints, and again, if you cannot decrease the length, it's because there's no angle, and then it has to be a smooth closed geodesic. Okay, so the length will go down unless the curve is a closed geodesic, And this map is continuous. So this map is continuous, so secondly, D of C depends continuously on C. And third, D of C is actually homotopic to C. Right? Because the change locally here, everything is changing in a convex ball. So I can always connect the two curves by geodesics because it's a convex ball. So D of C is homotopic to C, and the homotopy also depends continuously on C. So now we can prove Burkle's result, that there's always a closed geodesic. So first one has to show that L bar is positive. So here the idea is that if L bar is very small, then, okay, maybe I should say before. Okay, let's choose a minimizing sequence. So we choose a minimizing sequence. So what is that? Minimizing sequence is a family of sweep outs such that the sup of the length is converging to the optimal number. So it's, in this case, the sweep out is parameterized by a map. So it's going to be a family, a sequence of phis such that if I compute the sup of the length of the corresponding sweep outs, this is converging to the optimal number L bar. So choose a minimizing sequence, we can always do that. And then now, if L bar is very small, then every closed loop in the sweep out is going to have a very small length. So this means that the curve sigma phi k of t is going to be contained in a convex ball. It's contained in some convex ball. For all t and k sufficiently large. But if that is true, then so every curve in my sweep out, so this is my curve sigma fk of t, is going to lie inside some convex ball, but then I can just homotop my curve using minimizing geodesics. I can just deform it, retract it to a point. So this means that I can do a homotopy so that my map phi k is now going to be homotopic to a map phi k tilde, which goes from S2 to S2, such that this phi k tilde is constant in every curve of this type. Right? So for now, at each round circle like that, this map phi k tilde is going to be constant, and then it's easy to see, I leave it as an exercise, that phi k tilde has to be homotopic to a point. So the degree of phi k tilde is 0, and this is a contradiction. So if my curves, if the curves in the sweep out are very, very small, I can just homotop everything to a point. And then, of course, it's a contradiction. It's not a sweep out. So this implies that L bar has to be positive. So now I have to show that it's achieved as the length of a closed geodesic. So what I do is I have my minimizing sequence phi k, and I have my curve shortening map D. So what I do now is I consider the new family. For every k, I just apply D to my curve phi k. Sorry, the notation sigma phi k of t. So I take my sweep out, I apply D. This is going to be a new sweep out by broken geodesics. Okay? But the observation is that this is also a minimizing sequence. Also, the corresponding maps are also a minimizing sequence. Well, why is that? Well, because first, the length always goes down, right? So the sup of the lengths of these sweep outs now has to converge to a number which is going to be less than or equal to L bar. But it cannot be strictly smaller than L bar because these are sweep outs. So L bar is the optimal number. So again, the sup of the lengths of these guys has to converge to L bar. And now I applied a D again, I square. This is a new sequence of sweep outs, again by broken geodesics, again a minimizing sequence. Of sweep outs by broken geodesics. And then what I do, I look at this family of sweep outs. I choose curves that maximize the length, so I can choose some sequence of times in the interval 0, 1, so that the length of the corresponding curve tk is convergent to L bar. This is what we call a min-max sequence. So we choose a sequence of slices, curves in the sweep out, so that the lengths are going to L bar. So when I look at the curve, the corresponding curve in the previous family, D of sigma phi k of tk, the observation is that the length of these guys also converges to L bar. So why is that? Well, of course, the length of this guy is bigger than the length of this. So this sequence of numbers has to converge to something that is above L bar. But it cannot be strictly above because this is a minimizing sequence. So the sups are converging to L bar. So again, the sequence of numbers goes to L bar. But now, the advantage now is that this is a broken geodesic, so I can take a limit. Right? It's easy to take a limit of broken geodesics. So I can, by passing to a subsequence, I can take a limit. So these curves D sigma phi k of tk, they're going to converge to some broken geodesic C. Now, of course, if I apply D once more, these guys converge to D of C. But I know that the lengths of both sequence of curves are converging to L bar, so this implies that the length of D of C is equal to the length of C which is equal to L bar. But again, because D is a curve shortening, this implies that C is a closed geodesic. So you're able, in this way, of detecting some non-trivial closed geodesic C. Okay, so this is the proof. So I chose to do that because, I mean, of course, the high-dimensional situation will be much harder, but the principles are already here in this example. So let me, before moving on to minimal surfaces, let me just say a few more things about geodesics. Let me just check my time. So first, it's actually possible to show that there's always an embedded closed geodesic. Okay, so this is a theorem that we can attribute to Grayson in the 80s. Is it 80, 87 maybe? 89, yes. Here? So here I chose TK, right? So this is a sequence of curves, right? No. So sigma is a sweep out. So for every t, this gives me a closed curve. So it's a family of curves. So I choose one curve. Yeah. So this is actually a sequence of broken geodesics. Well, the advantage of going through D square is that both guys are broken geodesics, and it's easy to take limits. It's easier to take limits of a broken geodesic than of a general curve. Okay, so just because taking limits of a broken geodesics is just a elementary thing, because you just need to care about the vertices, right? That's only the reason why I do it twice. Okay, just so that this step becomes a simple thing. Okay, so the theorem of Grace is that every Riemannian S2 contains an embedded closed geodesic. So from now on, whenever I say a closed geodesic, I mean a non-trivial one. Okay. So the idea here is just to replace Birkhoff's curve shortening map by the parabolic curve shortening. Parabolic curve shortening. Which is just the equation given by, you would like to vary. You have an initial closed curve, and then you evolve the curve according to the curvature. And the reason why this is useful is because it actually, by the maximum principle, one can check that this preserves embeddedness of the curve. So if I start with a sweep out by embedded curves, I can evolve simultaneously the curves in my sweep out by the parabolic curve shortening flow, and they will stay embedded. And again, some curve will have to get stuck at a closed geodesic. Okay. So one can do that. And there's even a result which improves this. This is the optimal result by Lusternik and Schneermann. from the 30s, 37 maybe, actually 29, 1929, says that every Riemannian S2 contains at least 3 embedded closure basics. The key word, of course, here is embedded, and 3. And this is actually optimal because there are ellipsoids that have precisely 3 embedded closure basics. So the idea here is that one can actually do minimax over a 3-parameter family of curves instead of just a 1-parameter family. So the idea is that I can consider the following map from RP3 to the space of round circles. In Birkhoff's proof, right, you consider this 1-parameter family of round circles perpendicular to the x3 direction. But how about if you consider all round circles? So this is actually parameterized by RP3, because if you give me a point in RP3, I can associate the following geodesic circle, the set of points in S2 such that A0 plus A1x1 plus A2x2 plus A3x3 is equal to 0. So you're intersecting your S2 with the plane that gives you a round circle. So the space of round circles is really, just to find my color. It's really a 3-dimensional space. There's an actually RP3 family of curves. Right? So you can consider perhaps one could evolve these curves simultaneously by curve-shortening flow. And actually there is a theorem proven by Lustig-Schnirrmann that says that the basic fact here is that any function, say h, from RP3 to R, has at least 4 critical points. One of them is going to be the minimizing, so it's a trivial one, and then there are 3 non-trivial ones. So that's why you get 3 here. Okay, so this is Lustig-Schnirrmann theory, which is important because when I talk about minimal surfaces, actually there's going to be something similar. We're going to be talking about projective spaces. And finally, in the 90s, yes. Sorry, say that again. So I first proved that L bar is positive. Right. So first prove that L bar is positive, because if L bar is 0, these curves would be contracted to a point simultaneously, and then you get a trivial map, so it cannot be. So first you prove that L bar is positive, and then you do this. You get a non-trivial closure basic. It's two steps. Yeah. Sorry? Yeah, because otherwise the closure basic could be just a point. Yeah. Yeah. To make sure it's not trivial, I need L bar to be positive. So in the 90s, there's a theorem this. So the theorem by Franks 92 and Bangert 93, so almost at the same time. By combining the works of these two people, one can show that every Riemannian S2 contains infinitely many immersed closure geodesics. Okay, for embedded ones, the optimal result is 3 due to Luster-Schnuller. For immersed, there are always infinitely many. Okay. One drawback of that result, I mean, at least from my point of view, is that there's no completely variational proof of that. So one has to combine several cases, and one of the important cases that was done by Franks actually uses dynamics. Okay, uses the fact that one can talk about the geodesic flow. Anyway, the conjecture, I don't know who to attribute this conjecture, but is that every compact Riemannian manifold in any dimension, say MKG, contains infinitely many closed geodesics. And this is open. Okay? So the main difficulty here in the problem of closed geodesics is the iteration phenomenon. So the fact that if you give me, if gamma is a closed geodesic, so gamma is a map from S1 to M, then I denote by gamma to the power M, defined by EI theta is gamma of E M I theta. This is also a closed geodesic. So namely, if I have a closed geodesic given by a map from the circle to M, I can traverse it many, many times, right? And it's still a closed geodesic. But geometrically, they are the same object. So they are given by different maps. Geometrically, they are the same object. So when I say infinitely many here, I always mean geometrically distinct. So the danger is that you can produce infinitely many, but maybe these infinitely many are just given by iterations of the same curve. Have a question? Oh, okay. Yeah, sure. Okay, so that's the main problem. And again, for minimal surfaces, there will be a similar difficulty. All right, so now I'm ready to move on to higher dimensions. So actually, instead of a one-dimensional minimal surface is a closed geodesic. Okay, so now instead of considering a one-dimensional object, I will consider a co-dimensional one object. Okay, so let's move on to higher dimensions. And the case I'm interested in is when the object is actually something of dimension n inside a manifold of dimension n plus 1. So this is the hypersurface case. Okay, so again we have a variational picture. So we have the first variation of area. So it says the following. So if you give me a hypersurface sigma inside a Riemannian manifold, let's say this is sigma, I can evolve it. I can vary this sigma in some direction. So suppose I give my sigma by a map F, which is an immersion. I can consider a variation. So this is a map from sigma. Say this is F. Well, let's call it F minus epsilon epsilon into M. So this is a variation of F. So that means that F of x0 is just f of x. Maybe let's call it F naught. So I have a variation. Then if I differentiate with respect to t, the area of ft of sigma, this gives me the integral over sigma of the divergence of the velocity vector over sigma. So this is one way of writing the first variation of area. I will define this in a second. But if sigma is closed, which is the case I'm interested in, if the boundary of sigma is empty, then I can rewrite this as minus the integral sigma of the scalar product between the mean curvature vector and the velocity. So here, so the divergence of a vector field over a hypersurface is just given by the sum from 1 to n of the following expression. You differentiate x with respect to ei, take the scalar product with ei, where here ei is just an orthonormal basis of the tangent space to sigma. And the mean curvature vector, just recall that can be defined as, if you give me an orthonormal basis, I can sum the derivatives of ei with respect to ei, and then I can take the normal projection to sigma. So this is the mean curvature vector. It's a normal to the hypersurface. So again, this vanishing of this mean curvature vector, this is the minimal hypersurface equation, by the first variation formula is equivalent to the property that the first derivative of the area function is 0 for every variation. First derivative of the area is 0 for every variation. Okay, so this is a variational problem. So one remark about this higher dimensional setting is that one loses the dynamical point of view. Okay, so the remark is that no more dynamics. So the only method is variational. So the motivating conjecture, the conjecture of Yau, where is this? Let's see, I can erase this also. Let's see, what time is it? 12. So a motivating conjecture is a conjecture of Yau. (1982). So if you look at the famous list of open problems by Yao, this is going to be the first problem in the minimal surface section. Okay? Says that every compact, or close if you want, three-dimensional Riemannian manifold contains infinitely many smooth, closed, smooth, immersed minimal surfaces. So this was the conjecture. By the way, before I say more, let me just discuss one example, right? So I guess the simplest example of closed minimal surface is the equator in S3. So if my manifold happens to be S3 with the round metric, so this is the unit 3 sphere, then the equator is a minimal surface, okay? Second simplest example, again for round S3, is actually a torus. It's defined as S1 of radius 1 over square root of 2 times S1 over 1 over square root of 2. This is contained in the 3 sphere, and it's called the Clifford torus. Also a minimal surface. And in 1970, so this is a theorem that precedes Yao's conjecture, Lawson was able to show that there are, for the round S3, there are minimal surfaces of every genus. Okay? So there's actually a sequence of examples. Anyway, Yao's conjecture is for an arbitrary metric. So until very recently, the best result was actually due to Almgren and Pitts. So Almgren, 65, and Pitts, 1981, says the following. Suppose, okay, so it says that every compact Riemannian manifold, dimension n+1. So say the dimension is less than or equal to 7. So it includes the three-dimensional case, contains at least one closed smooth. And it's actually embedded minimal surface. So there is always at least one. This was the best result until very recently. And this guy is constructed by Minimax methods. So in higher dimensions, this is still true, but the hypersurface can be singular. So this is something that it's even true for the Plateau problem, that in higher dimensions, area minimizing surfaces can be singular. It's the same for the Minimax theory. So one remark is that if n+1, if the ambient dimension is at least 8, then one can find such sigma, but the singular set of sigma can exist, but it's small. So the Hausdorff dimension of the singular set of sigma is going to be at most n minus 7. So in low dimensions, the singular set is actually empty. So this uses regularity theory of Shannon-Simon. Okay, so as I said, a few years ago, I started working on the subject with André. So one of the theorems we proved is that one can actually improve 1 here to n plus 1. So there's, for an arbitrary metric, there's always at least n plus 1 minimal hypersurfaces. But recently, just a few months ago, we discovered that in the generic case, actually much more is true. Much stronger property holds true. So this is recent theorem. Let's call it the denseness. Maybe myself and Nevis, 2017, we proved the following thing, that for most Riemannian metrics, so let me say, okay, let me fix the manifold. So let n plus 1 be a compact manifold with no boundary. I suppose the dimension is in between 3 and 7. Then for most, let me say, for almost all Riemannian metrics, I will explain what this means. This is in the so-called, in the bare, the topological sense. For almost all Riemannian metrics, the union of all closed, smooth, embedded, minimal hypersurfaces is dense in the manifold. Okay, so this actually implies Yau's conjecture for generic metrics. This implies Yau's conjecture for generic metrics by proving this much stronger property. So in particular, we get that there exist infinitely many closed minimal hypersurfaces intersecting any given ball in the manifold. Intersecting any ball. Okay, so if you choose a metric randomly, for a manifold M, no matter how small the region you give me, there will be infinitely many guys, infinitely many sigmas intersecting that ball. Okay, that's the theorem. So, sort of a sequel paper, we actually proved a more precise result. I'd like to state here also. I can erase this. So in another paper, just also a few months ago, this is joint work with Nevis Song, I think is here in the audience, 2017. We proved the following. I'll call it the equidistribution theorem. We proved the following thing, that for, again, the same setting, so let n plus 1 be compact manifold, then again for a generic metric, for a C infinity generic metric G, this is the same. This is what I mean by saying for almost all metrics in the bare sense. Okay, for C infinity generic metric G, so almost all. In bare sense, there is a sequence sigma I of minimal hypersurfaces of connected minimal. Okay, so from now on, when I say minimal hypersurface, I will mean a closed, smooth, embedded minimal hypersurface. So there is a sequence of connected minimal hypersurfaces such that is equidistributed. Equidistributed in N. And what that means is that for any function, for any continuous function f on the manifold, if I integrate my function on the surfaces, I take the average and compute the limit, I will recover the global average of f. So if I take the limit as q goes to infinity, the following expression, so I sum up the integrals of f over the surfaces, and I divide by the total volume. So here I will use area or volume meaning the same thing. Okay? Sometimes I will write area, sometimes I write volume. It's the same thing. It's the n-dimensional area. So the limit of this thing is going to be 1 divided by the volume of n integral of f. Okay, so this is saying that equivalently, if I have my minimal hypersurface, this hypersurface gives me a measure, right? So the measure associated to sigma I is just the guy that, given open set, returns the volume of the surface inside that open set. So if you look at what I'm saying here is that if I sum up these measures, and if I normalize so that the total measure is 1, this is converging to the Lebesgue measure of the manifold. Normalized. This is converging to mu, where mu is just the volume measure. That's what it means to be equi-distributed. Okay. So those are the results. So equidistribution is something that, very come up in number theory or Garrick theory. I mean, this is really the first sort of result for minimal hypersurfaces. So are there any questions about the statements? So the main tool in the proof is this Weil law that we have proven 2 years ago. Okay, so the goal of the course, as I said, will be to give you a proof of that thing. But before that, let me just explain first what generic means. So if I take, so say that script M is the space of smooth Riemannian matrix M. So I put here the C-infinity topology. So this is a topological space. So I say that a property star is generic infinity generic M if the set of metrics that satisfy the property, matrix G that satisfy the property, contains a countable intersection of open and dense sets. Dense sets. So intersection like this. So each GI is open and dense. Okay, so this is what means to be generic. And the theorem of Baer's theorem says that generic implies, okay, so this is called sometimes it's also called the residual set. Such as the residual set, and what the theorem of Baer says is that residual actually implies dense. So being residual is actually stronger than being dense. So particular, given any metric, you can find arbitrarily small perturbations of it which have the property that the union of minimal surfaces is dense because of Baer's theorem. So the basic example of what generic set is, or residual set is if you take the real line, it would be the set of irrational numbers. So if you choose a random number, it's going to be irrational. So that's what it means to be generic, and we conjecture that both results of denseness and Equi distribution should hold in higher dimensions by allowing minimal hypersurfaces with codimension 7 singular set. Okay, so it should be a technical thing. There are some points in the proof that actually at this moment do not extend to higher dimensions, but we certainly expect that it should be true. For instance, the Weyl law that we use holds in any dimension. So let's see how many minutes. I have 15 minutes. Is the eraser here or here? So these hypersurfaces will be constructed by minimax methods. Okay, so what's kind of well known, I mean, for some people, is that one can talk about in higher dimensions. One can talk about one parameter sweep outs. And the easiest, I guess, the easiest way to produce a sweep out is by choosing a most function. So if you have a Riemannian manifold, M, you can choose your favorite most function, F. Maybe you can normalize it so that the image is the interval 0, 1. And then I can talk about the following family. For every t in the interval 0, 1, I consider phi of t to be the boundary of the set of points where f is less than or equal to t. So this is just, I was using the yellow color for sweep outs. This is just the sweep out given by level sets of my most function. Okay, so there could be, I mean, there are there's singularities, right? But it's okay because we're going to use geometric measure theory, so it's really, I mean, very weak notion of surface that we're going to use. And another very important difference is that in the problem of closed geodesics, we were always thinking of a closed geodesic as a map from the circle. Okay, this is going to change. Now there's no map. A hypersurface for me is really the image, like a closed object. Okay, so we don't really control, I mean, we allow different topologies. That's actually a very important thing. Anyway, this is an easy way of constructing a sweep out. But what's kind of not well known is that actually, this is a fact that I'm going to explain and I'm going to exploit, is that in fact there are non-trivial k-parameter sweep outs for every k. And these are families parametrized by parameter space. Like in this result of Lustenich-Schneermann, is going to be actually a projective space of dimension k. So I'm going to explain that. So somehow this fact was a bit, people didn't pay much attention to it. So with Andrea, we really studied that. And this is crucial for these results. Okay, so this is basically the introduction I like to give. I think I have still some minutes. Maybe, are there any questions? Yes, one question over there.
Are there any examples you know of where the set of
it's not dense? No, I mean, in principle, it could be true for all metrics. So, yeah. Yes. For any manifold. Any manifold M, any dimension. K can be bigger than the dimension. Yeah. So I'm going to explain that. Yeah. So actually, the space of surfaces is actually an RP infinity for every manifold. And I'm going to explain that. So so my first goal, okay, so what we're going to show is that, related to your question, is that if I consider the space of hypersurfaces, sigma n, that are the boundary of some region, I look at hypersurfaces that are boundaries, this space will be some kind of RP infinity. So it's going to be weakly homotopic to RP infinity. But in order to get there, I need to explain what this means and what the topology is. Okay, so let me try. Let me start now. I still have some 10 minutes. So we're going to use a concept coming from geometric measure theory. This is the concept of what a flat chain is. So flat chains. And in our case, the relevant ones are going to be the flat chains modulo 2. So this uses geometric measure theory. So one way of introducing these chains is by first considering polyhedral chains. So one takes some Euclidean space of big dimension n. You give me some k between 0 and n. This is an integer. Then I consider pk the space of k-dimensional polyhedral chains modulo 2. So a typical element, so an element P in pk is given by a sum of polyhedra, a finite sum, say of sigma I, where each sigma I is a compact convex k-dimensional polyhedron. And there is an equivalence relation. For instance, I say that sigma is equivalent to sigma 1 plus sigma 2 if sigma is the union of sigma 1 and sigma 2 along a common face. Sharing a common face. So for instance, if this is sigma 1 and then maybe here I have sigma 2, the whole thing is another polyhedron, then I say that the big thing is equivalent to the sum of these two. Okay, so this is what a polyhedral chain means. And then there's a natural notion of boundary, the boundary of a polyhedron. So the boundary of pk is an element of pk minus 1. And of course, the boundary of the boundary is equal to 0. Okay, so this is a group with a boundary operator. So if you want, it's a chain complex anyway. And then there's a natural notion of mass. Mass means the area, is a term for area in geometric measure theory. So you say that the mass of, say, P is going to be the sum of the volumes, the k-dimensional volumes of the sigma i's, but only if the sigma i's are non-overlapping. So we have a natural notion of boundary of what the mass is. And you also have some topologies. Let's see, just have some minutes. So there are several topologies one can put in that space. One is given by the mass metric. What it does is that the distance between two polyhedral chains is just the mass of the difference. So notice that this is a very strong topology. For instance, if you take, say, if P1 and P2 are intervals of size 1, and with distance epsilon, right? So these are two polyhedral chains at distance epsilon. The mass of the difference, the distance in the mass metric is actually going to be the sum of the masses. because there's no overlap. So it's actually 2. So epsilon can go to 0, but the distance is always 2. So it's a very strong topology. In order for two things to be very close to each other in the mass matrix, something like this should happen. Maybe P1 is like that, and maybe you can replace P1 by some epsilon region by something like this. This is size epsilon. This is P2. Then in that case, they are close to each other. The distance will be 4 epsilon in that case. Okay? So in order for two things to be close in the mass metric, they have to differ by a very small amount. So it's not such a good metric. But there is this other metric, which is the natural one. It's called the flat metric. Solves that issue. Maybe I will define it and I will end with it. So the natural topology to consider is really the flat metric, which actually goes back to Whitney. And the definition is the following. So the flat distance between two polyhedral chains is given by an infimum. So what you do is you take the difference between the two chains and you look at all forms, all ways of writing this as Q plus boundary of R. So Q is a K chain. R has to be a K plus 1 chain. You look at all Q's and R's so that this equation is true, and then you minimize the sum of the mass of Q plus the mass of R. This is k-dimensional volume. This is k plus 1 dimensional volume. So let's see the example number 1. So if I have, again, two intervals, P1 and P2, of size 1 and with distance epsilon. So what I can do is if I can define Q to be these two vertical guys. And by adding Q, the whole thing is the boundary of the rectangle, which I call it R. So I'm writing P1 minus P2 as Q plus the boundary of R. So that in that case, the flat distance will be less than or equal to the mass of Q plus the mass of R. Well, the mass of Q is 2 epsilon, and the area of R is epsilon, so this is 3 epsilon. So as you see, as epsilon goes to 0, these two chains become closer and closer in the flat metric. So this is really the natural metric to consider. Maybe just finish with one property, that the mass function, which is really the area, is not continuous with respect to this metric, but it's lower semi-continuous. With respect to the flat metric. So what it means is that if you have a sequence of polyhedral chains that converge in the flat metric to P, then the mass of P is going to be less than or equal to the lim inf of the masses of Pi. But it doesn't have to be equal. For instance, if I take, let me finish with this example. If I take P to be the square, say P is the unit square, maybe I take a square of size epsilon here, and then I erase this little square, and then I add maybe a tower here. So this is size epsilon. I guess this could be maybe the height here is 1 over epsilon. So in this example, one can see, maybe I leave it as an exercise. In this example, so this is P epsilon P epsilon is converging to P in the flat metric, but because the volume of this tower, the volume inside this tower is actually going to 0. The base has area epsilon squared, the size is 1 over epsilon, so the total, the three-dimensional volume bounded by the tower is going to 0. So P epsilon converges to P in the flat topology, but the mass of P epsilon is converging to, well, if I compute the area of this guy, I will have, I think, each side contributes area 1, so this is going to the mass of P plus 4. Okay, so the mass is not continuous with respect to the flat metric. This is actually good if your problem is a problem of minimization, because if you have a minimizing sequence, you take a limit. If the mass goes down, this is even better for you. But for a minimax, this poses problems. It's because, as you see here, the limit could have less mass than what you see in the sequence, so you can have loss of mass. So this is going to be one difficulty that I will discuss next time. Okay, so I'll finish here.